Now we will see some examples from the exercises. See, here in the example number 1 of the exercise, the information is given as that a circular coil of wire consisting of 100 turns each of the radius 8 centimeter and it carries a current of 0.40 ampere. Now we are asked that what is the magnitude of the magnetic field B at the center of the coil. Now actually for the center we have very well prepared equation. We can say first of all let's see what is given. So here in the case we are given that there is a coil and the coil is of 100 tons. So we can consider that it is like this. We consider it is made up of 100 tons. So here total tons that are N are 100. We can say that N is 100. Then it is given that the radius of each ton, that means this part we can consider like this. This is the radius R, and that is given 8 centimeter long. So radius is given, that is R is given 8 centimeter, that is 0.08 meter. Now another thing is given, that is a current. Electric current passing through this wire is considered as, say, I. We say it as I current is flowing through this, and we consider it like this. Suppose current is going in this direction, so that I is the current that is flowing through the circuit. So we can show it like this. Again we can show it like this, like this, like this, like this, like this, like this. So we consider that current is flowing in this coil. So we are given I here, that I is given as 0.40 ampere. So this is the value of current that is flowing through it, that is 0.40 ampere. Now we are asked to find out the magnetic field. Now obviously for the coil and its center we have the equation of B magnetic field, that is mu 0 into Ni over 2A or 2R. So this is the simple equation, and we are having all the values because we know that the value of mu 0 is about 4 pi into 10 to the power minus 7. We are given the value of N. N is here 100 number of tons. We are given current, that is 0.4 ampere, and the value, that is radius, that is 2 into 0.08. So when we put the values, we get the term to be, that is equals to pi into 10 raised to minus 4 as a whole. So this will be your answer, and if you want to write it in a unit, that is a Tesla, this can be also written as 3.14 into 10 raised to minus 4 Tesla. It can be also written as 3.14 Gauss, because Gauss is also the unit of magnetic field. So here we can cancel out the simplest term and we get the answer as 3.14 into 10 raised to minus 4 Tesla. So this is first answer and first question. In question number 2, that is more simpler and more easier than that previous one. We already know the equation for a straight wire. Here we are given that a long straight wire carries a current of 35 ampere. So here in this question number 2, we again consider a long wire. Say suppose this is a long wire and it has length, say infinite length. Infinite length means, again I am repeating because this is the most confusing term, that infinite length or a very long length means the length is comparatively very long than the radius of the cross section of the wire. So here a long straight wire that is given. Here I am showing that the current flowing through it, say 35 ampere, that is I is given, that is 35 ampere. We are also given that the magnitude of the field B at 0.20 centimeter from the wire. So now here in this case we have to find out the magnitude of the field at some distance. Say this is point P, and at this point P we are given a distance 20 centimeter. So from wire at 20 centimeter away, that is 0.2 meter. So 20 centimeter away we have to find out the magnitude of the magnetic field. Now we are also having the particular distance and the current. Now we know the value of mu 0, and we have again a very well popular equation of Ampere circuital law. If we consider that circular loop around the wire of given radius, as I have shown with the black dots. So if I consider the the Amperian loop around the wire, then I can apply the equation, that is B is equals to very well known equation, that is mu 0 into I over 2 pi r. Here we have this value as mu 0, that will be 4 pi into 10 raised to minus 7. Value of current is given, that is 35 ampere, and here 2 pi into radius, that is 0.2 meter. So we are given all these values, we have to find out and we have to solve this. So we can say that when we solve this, it is clear that pi cancel each other. Here 2 will cancel out with this 4 by 2. Here this is the value, that is 2 and 0.2, so that turns out to be a 10. So I can say that this will be a 10 multiplied by 35, that is 350 into 10 raised to minus 7. Now again when we simplify it, we can get this is equals to 3.5 into 10 raised to minus 5 Tesla. So this will be the answer of the example number 2. Now question number 3. What is given there in example number 3 that we will see now? So we are given that a long straight wire in horizontal plane carries a current of 50 ampere in the north to south direction. Give the magnitude and direction of magnetic field B at point 2.5 meter east of the wire. So here, now in this case, they have asked us two questions. Again here we will see one wire, long straight wire as previously stated. Now suppose from this long straight wire current I is flowing through it. I show it with a red color arrow. So the direction of current is given that the long straight wire in the horizontal plane carries a current of 50 ampere in a north to south direction. So suppose we consider that this is north part of the wire and this is south part of the wire. So current is flowing from north to south. It is given as per information. So we consider it as per information that the direction of current is given from north to south, and obviously from north to south is given. So give the magnitude and direction B at a point 2.5 meter east of the wire. Now we are having two more direction with respect to this north and south. If north is in my left hand side and south is in my right hand side, then I can say that east will be situated somewhere here and west will be situated somewhere here. Now we are asked to find out the magnitude field at direction east from the wire. So we are asked to find out the direction of the magnetic field and magnitude at point P. Say this is point P in the east direction. So I would like to write that direction name properly. That is east direction. That will be east, and this is west. This is north given in the left hand side and south given in the right hand side. So now we want to find out the direction of the magnetic field and the magnitude. Now magnitude is very clear and it is direct. As previous equation we have applied, we can again apply it. B equals to mu 0 I over 2 pi r. Here we are given r and I both. R is equals to 2.5 meter east, so 2.5 meter, and the current value is also given as a 50 ampere. So I is given as 50 ampere. Now when we apply these values and we find the answer, we get that is 4 pi into 10 raised to minus 7. Value of current is 50. Here 2 pi into r, that r is 2.5 meter. So when we solve this, we get again pi cancel out each other. Then we can have 2 2's are 4. Now 2.5 will have relation with 50, that 25 2's are 50, so 25 20's are 50. So here it will be something like 20. Now we have 40 in the question and this is about 10 raised to minus 7. So our answer will be, that is equals to 4 into 10 raised to minus 6 Tesla. So this is the direct magnitude of the magnetic field. Now we are asked the direction. Obviously, if we see the direction of magnetic field, then we will use the right hand thumb rule. As per as right hand thumb rule, it says that if the right hand thumb is in the direction of the current, then the finger curls around that wire will be the direction of the magnetic field. So now in the east direction as shown in the figure, the magnetic field will come out from that point. That is, direction of the magnetic field will be as this circular part on it and a dot sign that indicates that it is coming outward. While if the same question is asked at a west point, then we can say that it would go inside the plane and can be shown by the cross sign. So this is your example number 3. Now we will see the example number 4. In this example number 4, we are given that a horizontal overhead power line carries a current of 90 ampere in an east to west direction. What is the magnitude and direction of magnetic field due to the current 1.5 meter below the line? So here again the question is as exactly as previous question, but the direction and location are changed as per as the question requirement. Here in this question they have given that current is flowing from east to west in a wire. So a horizontal overhead power line carries a current of 90 ampere in east to west, so that I is flowing from east to west, and the value of current, that is I, is 90 ampere from east to west. Now what is the magnitude and direction of magnetic field due to a current 1.5 meter below the line? So now exactly below this line, if we go 1.5 meter away from it, say at this point P, which is at R distance, and R is 1.5 meter, 1.5 meter below the wire, we want to find out the direction and magnitude of the magnetic field. So again, for magnetic field, the equation is very clear, that is mu 0 I over 2 pi r. This is as per as Amperian circuital law. Now we are given values. Mu 0 is 4 pi into 10 raised to minus 7 into I is given here as a 90 ampere, 2 pi r, that is 2 pi, that is going to be cancelled, and r is 1.5. So in this case, what will be our answer? So we can say that the answer will be, again as in a previous question that we did, that is pi cancel out each other's effect. First thing, that is cancel out pi, then here 2, that will be cancel out, 4 by 2, 2's are 4, then 1.5 into, that is 90 in numerator and 1.5 is in denominator, so 15 6 are 19, so 1.5 6, that is 60, that is 60. So we can say that this is about 120. So the answer will be 120 into 10 raised to minus 7 Tesla. We can convert it into 10 raised to minus 5 Tesla, by writing it as a 1.2 into 10 raised to minus 5 Tesla, or it can be written as 0.12 into 10 raised to minus 4 Tesla, that is 0.12 Gauss. So this will be your answer. And now we move to the direction. Now to find out the direction again, let's observe the figure. In this figure, the current is flowing from east to west. That is, if we keep the thumb of right hand in the direction of the current flowing, so we can say that if the thumb is in the direction of current flow, and if we take curl about that wire, then the direction of magnetic field can be obtained using it. So if this is the thumb and it is having the direction of current, then the magnetic field will be divided like that. In upper part it will moving inside, so it will be like this, and in downward part it will come out from this. This can be explained separately. Now in our given region, if we apply it, that for our given region, if we apply it, then we can say that is here in our this given question we have the term that is current is moving in east to west. So we are asked to find out the magnetic field or the direction below the wire. So below the wire belongs to us for the south direction, and for the south direction it is coming out. So we can say that the current will come out from that, and we find that the direction of that field B will be towards south at a point below the power line. So it will come out, and come out, that means it is in the south direction, because as per as the arrangement, the upward part or inside part showing by the north, and the outward part or that outcoming part is given by the south. So here we can say that the direction of the magnetic field will be in the south direction as per as the question. Now we will see the next example, that is example number 5. Now what is given in example number 5, that what is the magnitude of magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30 degree with the direction of the uniform magnetic field of 0.15 Tesla. So here we are given 2 or 3 things, that uniform magnetic field is given, and that we can give by the arrow as shown here. Suppose this is uniform magnetic field, this is the direction of uniform magnetic field that is given here. Now we are having wire of current 8 ampere. This magnetic field is given B as 0.15 Tesla. So we are given 0.15 Tesla magnetic field. Now we are given, or we are provided one wire, this wire making an angle of 50 degree or 30 degree, sorry. So it makes an angle 30 degree with uniform magnetic field B So this magnetic field is uniform, and this is wire of say length L and having current that is 8 ampere in it. So it is having current 8 ampere inside it. I is given as 8 ampere, and angle makes with magnetic field is given by 30 degree. So we have to find out the magnitude and direction of unit and the direction of magnetic field. So here we have to find out the force actually. So in this question we have to find out force, and for that we have one simple equation, that is F is equals to IL cross B. Now I will use this equation by simplifying it. I will say ILB sine theta. Now in this equation we are provided all the things, that magnetic field is 0.15 Tesla, length that is not given, but we have to find out force per unit length. We are asked to find out force per unit length, that is to be find out. So here in this case we can say that small f is equals to force upon length, that is called force per unit length. What will remain now, that is I, B and sine theta. So this is the remaining term. Now we have to solve it. When we solve it, we get that small f is equals to the value of I, that is 8 ampere, the value of B, that is 0.15 Tesla, and angle that is 30, that is sine 30. Now we have to put all the necessary values, and when we put the values we get that this is 8, this is 0.15, and sine 30 is nothing but 1 by 2. So it will be around 4 into 0.15, that is 0.6 Newton per meter. So this is the answer. I am again repeating the question, that we are given that uniform magnetic field and one wire of 8 ampere aligned at 30 degree with this uniform magnetic field. The value of uniform magnetic field is given by 0.15 Tesla, and for that we have to calculate this question, and we apply the equation, that is force is equals to IL cross B. By applying this equation we can apply the value of different given quantities, and when we simplify we get that force per unit length is given as IB sine theta, and it is equals to 0.6 Newton per meter. So this is for the example number 6. Now question number 6. In this question number 6, again we are provided an interesting information in a different way. See, generally we are used to consider that if we are given solenoid, then we have to apply the equation of solenoid, but this is a special type of confusing question, and so I would like to put in a term of important question, that is IMP question, because it is a confusing question. Generally when we read solenoid we find that here the equation of solenoid, that is B equals to mu 0 Ni, is to be applied, but no, here this is not that type of question. Here in this question they have given, first of all we will read this information, that a 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. So here with a blue line I have shown the solenoid. For solenoid we know that the direction of magnetic field is always on the axial part. So here I have also shown the axial part with that magnetic field is moving towards the upward direction. So here that magnetic field is given by that green color part. So here green color indicates the uniform magnetic field. So green color indicates uniform magnetic field that is given of 0.27 Tesla. So B is given, that is 0.27 Tesla. Second thing, we are also given a wire of 3 centimeter length. So the length of the wire is given 3 centimeter, which consists current of 10 ampere. So we are given a wire of 10 ampere, length 3 centimeter. And now what we are asked to find out? We are asked that what is the magnetic force on the wire, this small wire which are we given here. We have to find out the force acting on this black color wire. Now very interesting, here solenoid is given, but we are not going to use equation of solenoid. Instead that what we will do, we will apply the magnetic field equation of solenoid. Instead we apply the force F. So we force F is equals to IL cross B is a popular equation. Here generally we say that this is equals to ILB sine theta. Now in the question we are indirectly given direction also. I have also shown it by drawing a figure, but I am separating it now. Say this is direction of magnetic field in the axial line, and this is suppose current carrying segment. So current carrying segment is lying over here, and the angle between them, that is theta, is 90 degree, and therefore sine 90 will be 1. So this sine 90 will be 1, here theta will be 90. So when we put all the values over here, we will get that the equation में जब हम वैल्यू रखेंगे, we will get that I is equals to 10 ampere. So I is equals to 10 ampere. Length is given 3 centimeter, that is 3 into 10 raised to minus 2 meter. The magnetic field is 0.27 Tesla. So this is 0.27 Tesla, and sine 90 is 1. So when we simplify it, we simply get that it is 8.1 into 10 raised to minus 2 Newton. Now suppose I want to find out the direction of this force. So to find out the direction of the force, what I will write or what I should do? So for that you has to remember the equation or the phenomena of the Fleming's left hand rule. Now up to yet we are always used to apply right hand thumb rule or right hand screw rule or only right hand rule, but now we have to memorize that Fleming's left hand rule. If you remember that what is Fleming's left hand rule, we can say that Fleming's left hand rule state that if the direction of magnetic field is in the direction of the pointer, so this magnetic field will indicated by the pointer. If direction of the current carrying segment is indicated by a big man, so a big man finger, if applying the direction of current, then the direction of the force will be perpendicular to both of them in the direction of the thumb. So this is called the Fleming law. So if this is pointer, this is big man, then the direction of the thumb like this would be the rule. So this is pointer, this is big man, pointer has a magnetic field, big man has a current, so the thumb will have the direction of force. So this is called Fleming rule, Fleming left hand rule. So we have to remember it properly, and it is applicable to the terms. So this is the left hand rule of the Fleming, and that is your memory. You have already studied it in your 9th or 10th standard. Actually this is not the question they have asked, but as we go with that question, we must know that what is the term given.